In this series, we're exploring multiple ways that we can solve circuits using different techniques. Now in the first video, we simply built the circuit below and measured the voltages and currents with a multimeter and saw what we got. That's one way to solve a circuit. We're going to solve the same circuit a bunch of different ways now. In this video, we're going to use Kirchhoff's laws to do it analytically. Then we're going to use superposition, then Thevenin equivalent circuits, and finally we'll simulate it. But let's recall what we had when we made our measurements in the last video. So if I recall correctly, we found that we had half a milliamp flowing upwards. We had 2.5 milliamps flowing downwards, and we had 2 milliamps flowing upwards. And if we took out our multimeter and we measured the delta V, the voltage, between points A and B, we found it was 5 volts. Okay? So let's try to derive that a different way. Not by building the circuit, but by using Kirchhoff's laws. So for Kirchhoff's laws, there's several approaches that we can apply. We can just concentrate on the nodes, we can look at a bunch of loops, or we can take different combinations. In general, we're going to find that we have more equations than we need, so we can just pick whatever is convenient. So let's do that. We're going to start working through this circuit here. So the first step in the Kirchhoff approach is we're just going to solve for our currents. But the problem is we don't know which way they're going. That's fine. We're just going to guess random current directions. We're going to identify and label all the unique currents and identify them. And if we get the wrong direction, we just guessed it wrong, we'll just get a negative. Because remember, 5 milliamps going to the right is completely equivalent to negative 5 milliamps going to the left. If we just think about it, how much charge per second is flowing through a point. So let's pick our random arbitrary current directions. We're going to label I1 here, I2, and I3. Why not? And that's step one there. I mean, we can go a bit further. We can look at it in terms of Kirchhoff's current law. And what does it tell us there? So I'll say what we're actually doing here. We're labeling all currents, and then we're going to apply Kirchhoff's current law. So Kirchhoff's current law at node A here, it tells us that, we'll say at A, will tell us that we have I1, because I1 is going into the node, plus negative I2, so minus I2, plus negative I3, I3 is also leaving, is equal to 0. Or in other words, I1 is equal to I2 plus I3. How about at node B? Well, at node B, we have a similar situation. Note that we have current I2 going all the way around this loop. So we have I2 here. And we similarly have I1 here. So at B, Kirchhoff's current law says that negative I1 plus I2 plus I3, I3 and I2 are going into the node, is equal to 0. And that's also I1 is equal to I2 plus I3. So let's highlight this equation. And that's our first thing we've learned about the circuit. We'll just move that down there. Now let's move on to the second part. The second part of Kirchhoff's laws, which is to apply the voltage law by looking at the different loops where we have all the voltages, the voltage gains and the voltage drops that need to add up to 0. So we'll call it step 2. Identify the voltage loops. So let's look at the potential loops we have here. We'll take our charge, our test charge here, and we'll just drag it along the circuit, starting at the top left. One loop, one potential loop looks like this, L1. We could also kind of take the outer path. Let's see the cleanest way to do that. So we're going to go along here, and we'll call that L2. And we can also take another loop, L3. These are all the potential loops that we have in our circuit here. So by applying these loops, L1, L2, L3, we can actually systematically solve for all the currents and voltages in this system. So let's do that. Let's look at L1 for now. So applying these loops, we're going to get voltage gains and drops. And we have to be a bit careful about whether or not an element is a gain or a drop. So there's only a few cases that we need to worry about. Remember that if we have a battery, and we go from A to B here, along a loop. There's our loop. A battery with voltage V. We are V volts higher at B than we were at A. That's what a battery does. That's what a voltage source does. We raise the potential by V volts. So that's going to be positive. If we're going the other way through a battery, we have the same battery, but we just happen to be looping backwards through it. Well, I'm going to have a lower voltage because I've gone from a higher to a lower potential. So as I'm dragging my charge along the circuit there, it's going to lose potential. There's also the drops across the resistors. So if I have a resistor and there's current flowing through it that way, and I'm going across in my loop like this, well, this is Ohm's law. This tells us that I'm losing IR as I go from point A to point B. In fact, my voltage loss, my net gain, or loss in voltage, is minus I times R. I've lost IR volts across there. So that's also negative. Finally, if I'm going from A to B, and the current is going the other way, well, I'm actually at a higher potential at B than I would be at A. This is a voltage gain. In fact, the way we've drawn it, we kind of have a quadrant here. We can do this. All our voltage changes will be positive in the top and negative on the bottom. And these are the only things we need to worry about. So let's have a look at the first voltage loop here. Starting at the top left corner, we're going through a battery, through a 2K resistor, through another 2K resistor. I'll just redraw it here. That's what it looked like. Let's just move it over here. Well, let's just do the accounting. So we're just going to start here, and first thing we do is come across a battery. We're going in the positive direction across it, so we have 9 volts, and we're going with the current through a resistor, so it's negative, minus 2 kilo ohms times I3, and we're going to subtract another 2 kilo ohms times I1, and that equals 0. So all of that stuff has to add up to 0. That's Kirchhoff's voltage law. And we're going to apply a little shortcut here. We're going to work in units of volts, and we'll use the units of current to be milliamps, and the units of resistance to be kilo ohms, so that IR is also in volts. The units of IR is 1,000th of an amp times 1,000 ohms, which is just 1 volt. And we can just not write units. We've got to be careful when we do this, but it's going to, when you're doing systems of equations, units get really cumbersome. So let's write this out. And this is equivalent to writing 2I1 plus 2I3 is equal to 9. Much cleaner. Okay, that's great. Let's apply a different loop now. Let's go to loop 3. We could have done loop 2 as well, but let's just mix it up a bit because this is going to be fairly instructive. Let's redraw that now. Okay, so this is our loop. Let's do the same kind of accounting, starting here. So we go across the battery, but we're going the other way across it now. So we have minus 6. We're going along the current with the resistor, so we get minus a standard voltage drop, 2I2. But now we're going the opposite way across the current. The voltage is higher at the top than it is at the bottom, and we're going to get a plus 2 kilo ohms times I3. And this tells us now 2I3 minus 2I2 is equal to 6, because, as I forgot to write, this whole thing is equal to 0. That's Kirchhoff's voltage law. Okay, So we're going to do one thing. We'll circle this equation and this equation. We'll call it 1 and 2. And what we'll do now is we'll use Kirchhoff's current law. So we'll go use I1 is equal to I2 plus I3 into equation 1, and we find that we have 2I2 plus 4I3 is equal to 9, and 2 says negative 2I2 plus 2I3 is equal to 6. Well, that's convenient. We can just add them up, and we get 0 here, and we get 6I3 is equal to 15 units of volts, and therefore I3 is equal to 15 over 6. 15 over 6 is 2.5. Let's plug that back into equation 1, and that will tell us that, let's see, 2I2 plus 4 times 2.5 milliamps is equal to 9. This whole thing is equal to 10. So that 2I2 is equal to negative 1, or I2 is equal to negative 0.5 milliamps. It's negative. What does that mean? Well, remember that we guessed I2 is going downwards to the right here. This is what we thought I2 was doing. But in fact, we got negative 0.5 milliamps, so in fact, it's plus 0.5 milliamps going upwards. Okay, let's just wrap that up. We can use Kirchhoff's current law now to find that I1 is equal to I2 plus I3, and that's equal to negative 0.5 milliamps plus 2.5 milliamps, and that's 2 milliamps. So that I1 is equal to 2 milliamps. And that's all the currents in the system. So let's redraw that circuit, or just copy and paste it, and find that we had 2 milliamps this way. We had half a milliamp plus a half a milliamp this way. Remember, we solved and found it was negative 0.5 milliamps going down, which is the same as half a milliamp going up. And we had 2.5 milliamps going down. And there we've completely solved all the currents. If we want to get the voltage drops across the resistors, we can just apply Ohm's law. For example, if I want the voltage between A and B, well, it's just IR. So it's I3, we called it, times 2 kilo ohms, or 2.5 milliamps times 2 kilo ohms, and that's equal to 5 volts, which, if you recall, is exactly what we found. So that's the second way that we can solve for all the quantities in a circuit. We could go further. We could find, just offhand, we can even do it in our minds. We can even do it in our heads now. The voltage drop across this resistor, this 2K resistor, is 2 milliamps times 2K, 4 volts, or negative 4 volts from top to bottom, exactly what we found. And we have half a milliamp times 2 kilo ohms on the right here, which is going to be our negative 1 volt as we measured it down, which is what we found when we measured the circuit. Okay, so that's it for the Kirchhoff method. Next time we're going to try a new method. We're going to use the linearity of circuits in a technique called superposition.